Hi, Mr. Zentner. As you may know, my name is Ricardo, and this is my project on vectors. And in this video, I will explain what it do. It's basically a point that no matter how much you move the structure, it stays in place in the space. And I will also show you where the criteria is on that. So first, we need to identify a point, and who's better than the man himself? Within point to do that job. Thank you, Brendan. You know, there's points everywhere in the structure, but you know, this is the best point in my opinion. Brendan will also show us where the null vector is, which would be around here, since this is the place where it all starts. So the plane starts here at 0, 0, over here. Also, if you check a bit closer over here, you can see that the vector, the positive vector here would be equal to A, and the negative version of the vector would be equal to B. In the same kind of spirit, the vector C here, whether it's positive or negative, will remain C because its position will not affect the structure, since it goes from here to here, and from here to here. If we look at this part of the structure, we can see that many criteria are present on this specific part. Notably, the number 6, which is x minus w be equal to d, and number 7, which is close to none to the vector d, is the vector r multiplied by a scalar k would be kr. Not far from here, right here, you can observe the 2D normal vector, which is present here, 90-degree angle, and on the other side, a 3D orthogonal vector. As you may see, here it comes out of the structure. Version alternative. The now let's jump towards the arms with the triangles, since all of the other criteria are situated somewhere around here. Notably the number 5th, which is S plus V is equal to Z, which could be seen basically anywhere in the arm, since this is a vector, and this is a vector, and this is a vector, and if you do this vector plus this vector, it will be equal to the resultant of a vector which could be from here up to here, and adding up here, adding up here, adding up here, until here from here. So for the triangle parts, many parallel vectors can be observed. Most notably, this vector and this vector, who will never ever touch since they are parallel. And if we also check on a near triangle, you can observe the unit vector, which would be like, if let's say the magnitude of this vector would be 4, well, the unit vector would be 1, would be 1, 2, 3, 4 unit vector. It is also possible to observe dot products on any triangles, because if you want to find the angle, well, any angle in the triangles, you will need to do the dot product. If you want to find this angle, you need to do the dot product between these two vectors. This angle, dot product between these two vectors. This angle. Now for the parallel and orthogonal projection. Let's say this part of the triangle right here, the parallel projection would be the x component of the vector here, and the orthogonal projection would be the shadow on the other triangle, which would be the y component of the vector. For rotation and transformation, when you move the structure, you can see, let's say like this point here, this vector has a rotation movement added to it. See how it just moves like that. And for transformation, if you see the length between these, it gets shorter and shorter, so it transforms the length between these.